right. The This lesson today is about power and efficiency, called the power of physics. So really, what we're going to do today is define power, what it is, what it represents, and how you calculate it. And as well, we're going to look at the efficiency of a system. So how can we calculate the efficiency of a system, whether or not all the energy is going to useful forms, and how much is being lost. So it's actually a very simple concept, but very powerful. Joke intended. All right, so power. And I would take notes on this, obviously. Power is simply the rate at which work, and remember, work is the change in energy, delta E, right? So it's the work is the change in energy. So it's the rate at which work is done. So the term rate you learned in grade 9 and 10 and even in 11, it simply says the number of units per another unit. So the rate at which something happens. So like rate of speed is meters per second. So the same thing here, work is the change in energy over time. So we give the symbol for power as P. The work done, remember, is just change in energy. This could be kinetic energy, this could be gravitational energy, this could be thermal energy, this could be chemical energy, this could be anything you want, any change in energy. So the final energy state minus the initial energy state, so how much work is done divided by the time. So this says how many joules of work or energy change happen in a given amount of time. So the units for this are joules per second. Joules is on the top, seconds is on the bottom. It's that simple. Now, we don't always write it as joules per second. We name this after James Press, this guy named Watt, and what was his last name? So we name them watts, and the symbol is W. Now, don't get this W for the unit confused with work. That's why I wrote this as delta E up here. Sometimes people write W, but then it gets confusing with the symbol for work. So the change in energy over time is joules per second, or what we call a watt. Now, many of you would have seen the term watts before. When we talked about power in the electricity unit, we said, oh, this is the number of watts, so it was joules per second. So we'd seen that before. Also, if you have a stereo system, you say, oh yeah, that's a 100 watt. Well, I wouldn't want to have a 100 watt system, but so a 100 watt system, or a light bulb. You know, those new incandescent, or so the new fluorescent bulbs are 10 watts. That means that they use 10 joules of energy every second. And a 100 watt light bulb uses 100 joules of energy every second. So that's the power output. We can also measure the power output of objects. So let's say that a person lifts a dumbbell. Let's say they lift 100 pounds and they lift it from their shoulders to 20 centimeters over their head. Let's say they lift it over their head. If someone else lifts the same 100 pounds, the same distance, but does it faster, they are more powerful, because the faster you do it, the lower the time. The lower the time, the bigger the power. And we'll show it on the next slide. So if you want to maximize power, how do we do that? Well, maximizing power is, and you can see the term power is written up there. You can't see it. It's P-O-W-E-R. So maximizing power. In order to maximize power, what we do is, this is offset. This delta E should be right over top of this here. So we take the change in energy and we make it huge, and then we make the time really small. So we do a lot of work or a large change in energy in a short period of time. Okay, so that delta E should be over top of there. Do a lot of work, large change in energy in a short period of time. If you want something to be less powerful, do a small amount of work or change in energy and take a long time to do it. And that's basically it. So if you take a long time to lift a dumbbell over your head, say 100 pounds, you're less powerful. But if you do it really quick, you're powerful. All right, that's it for power. It's that simple. The rearranging of that equation is very simple as well. We'll see that in some examples. Efficiency. Well, efficiency is really important. So we know this from before, that when energy is transformed from one form into another, what we call work, none of the energy is destroyed. That's the conservation law. However, some is transferred into non-useful forms of energy, heat, sound, the forming of the object, things like that. So the goal of most engineering companies and businesses is to improve machine efficiency in order to reduce waste energy. So you might want to pause at this point, write this down, and then continue after that. Light bulb. Okay, and the word efficiencies is very, it's pretty much white there, so let's just say light bulb efficiencies. An incandescent bulb, so this is just to show you that if you put 100 joules of energy into an incandescent bulb, okay, every second, so that would be 100 joules of energy every second. Of that, 10 joules, only 10, will go to light. The other 90 joules, or 90%, is actually waste energy. It actually comes out as heat. If you've ever touched an incandescent bulb, you know they get really hot. And they could heat up a room if you have enough of them in a room. So you can feel that heat. So that's bad in terms of efficiency. So if there's 100 joules coming in and 10 gets used, and that's useful, and this 90 joules is waste, 10 divided by 100 times 100% gives you 10% efficiency, because it's 10 units per 100 units, and that, I mean, percent means per 100. So 10 per 100 is 10%. And our waste would be 90%. It's a good little graphic. You may want to jot this one down in your notes too, just to give you an idea of what's happening. You don't have to make it as fancy. Now, compact fluorescent bulb. Okay. Put 100 joules of electricity in, you actually get 75 joules of light. And then only 25 joules of heat energy. 75 per 100 is 75%. So these are 75% efficient. That's why there's been this big switch to these compact fluorescent bulbs, because more of the energy goes to light and less to heat. And you can actually touch the, well, I wouldn't suggest it, but they don't get as hot as an incandescent bulb. You can actually get LED lights, which are almost 100% efficient, and you can touch them. They don't even get hot at all. An LED TV, basically, you can go up to it and it feels cold because there's no heat coming off from it. Whereas if you go to an old TV, like a compact fluorescent TV, or sorry, a tube TV or an LCD TV, a rear projection TV, things like that, you'll notice a lot of heat, and they're less efficient because less useful energy. So we're talking here about the useful energy to the total energy input. So how much useful output energy to how much input energy? 75 to 100, or 75%. So write this down. This says efficiency equation. The ratio of input energy to useful output energy is a measure of the efficiency. So that's what I said in the last slide. The input energy to useful output. The input energy to useful output. So what's useful output? Well, on the last slide, useful output said 75 joules. How much was input? 100 joules. 75 divided by 100 is 0.75 times 100, 75%. And that's how you calculate efficiency. Look at how much useful output you get and divide it by how much you put in. 100% efficiency would be if you get 100 joules out and you put 100 joules in, you're 100% efficiency. There's no waste energy. Never happens. Typically, it's quite low. Most efficiencies are surprisingly low. Okay, that's it. And now we'll move on to the other activities.